This is the review video for Essentials of Adaptive Immunity, and let's get into it. So the Essentials of Adaptive Immunity was several different diagrams and lists, and one of them is lymphocyte. And what is a lymphocyte? The way we draw a lymphocyte reflects its true nature, where it has many copies of one single receptor called its lymphocyte receptor. It's either, if it's a B cell, it has a B cell receptor, and if it is a T cell, it has a T cell receptor. And the receptors are different. T cell receptors are not like B cell receptors, except that they are randomly generated. And the whole adaptive immune system depends on figuring out which lymphocyte we need, which one has the right receptor. Because every lymphocyte has a randomly generated receptor. It may have 100,000 copies of it, but it's still just that one. And we don't know where it is. And many lymphocytes will never do anything. Many lymphocytes will never detect anything because their receptor will go unused. They will never see the thing they're supposed to see. And we can get into that a little bit when we do lymphocyte development, where we start with an immature lymphocyte, go through education, and the majority of lymphocytes die. Only 5% of them survive this process to become mature, naive lymphocytes. And these wait. That's their whole thing. They wait. This is the majority of the lymphocytes in your body. They are just waiting to be activated. If they go through activation, and it's like less than 0.1% of these ever go through activation, then they become active or activated. There isn't really a term for that, but it's useful for us to think of it. And then that lymphocyte, once it gets activated, goes through clonal expansion. It divides, and its daughters divide, and its granddaughters divide. They divide as fast as they can. And then the last thing is differentiation, where some of those descendant cells become effector cells, and others become memory cells. Yeah, we just got a weird error message. You know what's even weirder is when you put it on like a rainbow, and it shows you rainbow. Did it start working? Oh my God, it started working. That would have been really useful when I was trying to draw a biofilm, but it wouldn't work then. Anyway, that's lymphocyte development, and this is an illegible scribble because you're supposed to know it already, and hopefully you were testing yourself as we went. Then the next topic was antibodies. I think, I don't remember. Antibodies is one of the topics, and what we have to think about is antibodies are proteins. Each antibody is made of at least 4 proteins. There are 2 heavy chains. Why are they called chains? And 2 light chains. So the heavy chains are these long ones, and the light chains are these. And those chains, well, that's 4 separate proteins. And then on the end of each chain, oh, this is terrible because they're supposed to match. Yeah, those are supposed to match and they don't. So I can't use my cool colors. I just have to use like colors. So here the heavy chains have blue hypervariable regions and the light chains are going to have pink hypervariable regions. And those are the randomly generated parts of the antibody. So these are hypervariable regions. And the purpose of those is to make a brand new randomly generated binding site. Binding site. Antibodies are very similar to B-cell receptors, and receptors have binding sites, and so do antibodies. The difference is antibodies stick to something, and that is their whole job. You also have the FC part, or the FC fragment. And that is something that many cells in the bodies have receptors for. Because if they detect an FC part, it means whatever they're looking at has antibodies stuck to it. So those are the parts of an antibody. You've got the heavy chain, the light chain, the FC part, the binding site, and the hypervariable regions. That's pretty good. And then you need a list of antibody functions. And I'm going to list the ones I can remember off the top of my head. Opsonization is a big one. Another big one is neutralization. Another is agglutination, which I think has 2 G's and 1 T. Agglutination. Antibodies can also do antibody-dependent cell-mediated cytotoxicity, where they mark one of our own cells to be killed. They can trigger complement cascade. And I have to look up the 6th one because I don't remember it. I have not been trying to memorize this, tell you what. Okay, I went away and I looked it up, and I'm not surprised I forgot about it because it's something I didn't really think about much before, which is degranulation. And this, again, would be where an antibody has marked a worm or something to be killed by a granulocyte. So that's cool. In a lot of cases, antibodies are just little markers that show the immune system what to attack. That's degranulation, that's antibody-dependent cell-mediated cytotoxicity, that's other opsonization. And in some cases, just by being there, they can stick things together or block them. That's agglutination and neutralization. And they also have something that basically acts kind of like an enzyme. It's not an enzyme, but it does something very active in triggering complement. And again, it's because some of the complement proteins have essentially FC receptors. But they're just proteins. So they don't have receptors. They might be receptors, or they might have receptor parts of a protein. So the antibody does something kind of unique here in triggering the complement system. Anything else? I'm just trying to think of what else. I'm just scrolling through. Oh, right. Effector cell functions. This is big. Effector cell functions. The two effector cell types that do the immune response and go out and do important things directly are CD8 positive cytotoxic T cells, that's one. And its function is to kill infected or cancerous cells. And plasma B cells, which make antibodies. So all those antibody functions happen because plasma B cells make the antibodies, and we haven't really looked at cytotoxic T cells, but they are what ends a viral infection in a human. But then a much bigger group of effector cells is the CD4 positive helper T cells. And what all helper T cells do is push the immune response towards an outcome, like towards an antiviral outcome or an antiparasitic outcome or antibacterial. And they do this by releasing signaling molecules. There are many types of helper T cells. They adopt a type when they get activated. So there's something attacking the body, and the innate immune system is releasing a bunch of signals. Mature but naive CD4 positive T lymphocyte gets activated, and it senses those signals from all the innate immune cells. It senses the signals and figures out what type of helper T cell it should be. That then determines what chemical signals it sends. And those signals are felt all over the body and guide the immune response. But another thing they do is activate B cells. And then there are some other things that some of them do. So I'm going to put a little dot here because they don't all do all of these things. But as far as I know, they all do these things. They all push the immune system one way or the other. They all release a huge amount of their own specific type of signaling molecule, and they all activate B cells. Some activate macrophages. They activate macrophages. Some license dendritic cells. And that allows the dendritic cell to activate CD8 positive T cells, which will become cytotoxic T cells. So that's a whole big deal. Without helper T cells, we don't get plasma B cells or activated macrophages or cytotoxic T cells. Some of them guide affinity maturation, and that's the process of improving our antibodies over the course of an immune response. And then the final effector cell is the CD4 positive regulatory T cell. And its job is to slow or stop part of an immune response. And that is the review of the essentials of adaptive immunity. So make sure you go back and check that out. And if you were a step ahead of me this whole time and you remember the things I didn't, congratulations, you're in good shape. But it is a lot of stuff to remember. And again, we will use all of this when we think about immune responses in Unit 3. We will think about all of this stuff. because we're going to look at some more nuts and bolts of how the immune system works, and all of this will come back. So that's a unique part of this class, is how much we have to keep going back as we learn new parts of the immune system. So I will see you when we do that.